What does it mean for a machine to last longer than the world that built it? In the quiet corners of museums and private garages, there are engines that still turn, still breathe, still hum with purpose, long after their moment passed. They are not legends because they failed. They are remembered because they worked, sometimes too well. This story begins not with collapse, but with endurance. Imagine the early morning light falling across a factory floor. Steel frames wait in rows. Blueprints curl at the edges. Engineers linger, hands stained with oil, eyes bright with the hope that this time they have solved something fundamental. Not just speed or power, but longevity. They are chasing a different dream, an engine that refuses to wear out, a system that treats energy with respect, a machine that does not demand constant sacrifice from its owner. The 20th century was built on motion. Cars promised freedom. Distance collapsed. Cities spread outward. Yet beneath that promise sat a quiet compromise. Machines were expected to age quickly, to need attention, to invite replacement. Reliability was celebrated, but only up to a point. Beyond that point, durability became inconvenient. A thing that lasts too long can unsettle the rhythms of an economy designed around renewal. This documentary is not an accusation. It is a meditation. Across decades, inventors and engineers repeatedly asked the same question: what if we built engines to endure? What if efficiency were not incremental, but transformative? What if fuel were flexible, maintenance minimal, failure rare? In laboratories, workshops, and test tracks, answers emerged, sometimes briefly, sometimes imperfectly, always human. Some of these ideas appeared at moments of transition: the dawn of mass production, the rise of oil as a global artery, the anxiety of energy shortages. Others surfaced quietly, almost accidentally, as byproducts of curiosity. A lighter material here, a different combustion geometry there, a motor with fewer moving parts. Each innovation carried with it not just technical promise, but cultural weight. What followed was rarely dramatic in the way movies portray. More often, it was subtle. A project paused, funding redirected, a prototype shelved, engineers reassigned, explanations varied, costs were too high, markets not ready, infrastructure incomplete. Sometimes these reasons were true, sometimes they were convenient. History is rarely shaped by a single hand. It moves through systems, economic, social, psychological, that reward certain outcomes and discourage others. We live surrounded by machines that ask for our attention. Oil changes, tune-ups, repairs, replacements. We accept this as normal, even natural. But it is worth remembering that it is also designed. Not designed by villains, but by incentives, by habits, by the quiet agreement between what is possible and what is profitable. The engines we will encounter in this journey are not miracles. They are not perfect. Some were rough, some incomplete, some exaggerated by memory. Yet each one points to a recurring human impulse to build something better than required, to push beyond adequacy, to imagine a future where technology serves time rather than consuming it. As we move through these chapters, we will return again and again to a simple tension. Discovery meets doubt. Promise meets practicality. Innovation meets the world it must live in. And at the center of it all stands a question that still hums beneath modern life. When something works too well, what do we do with it? This is not a story about engines alone. It is about choice, about what societies nurture and what they quietly let go, about the difference between progress measured in quarters and progress measured in generations. The machines endured. The question is whether we were ready for them. It began with a promise and a roar. In 1948, Preston Tucker stood beside a gleaming, bullet-shaped automobile and offered the American public a glimpse of the future. The Tucker 48 was unlike anything on the road. Sleek, aerodynamic, bold. But the car's true heart, hidden beneath its rear hood, was even more revolutionary. A flat-six engine, lightweight, powerful, and built to last not years, but decades. Designed by Ben Parsons, the Tucker engine used aluminum blocks and heads at a time when Detroit was still pouring heavy iron. It employed hemispherical combustion chambers for cleaner, more efficient burns. Hydraulic valve lifters eliminated the need for constant adjustments. Most engines of the day struggled to reach 50,000 miles without a rebuild. Tucker demanded 150,000. The prototypes delivered. Test engines ran continuously, never breaking. They produced more power, burned less fuel, and weighed less than their competitors. Tucker wanted to build 50,000 cars in the first year. He had 150,000 orders. Americans were hungry for a vehicle that didn't just drive. They wanted one that endured. But that very endurance triggered fear. Detroit's giants, Ford, GM, Chrysler, saw not a car, but a threat. If Tucker's engine reached the market, it would reset expectations. Why accept planned obsolescence when you could have a car that didn't break down? Why tolerate clunky inefficiency when smooth reliability was possible? Tucker's creation didn't just challenge the industry's technology, it challenged its business model. The response came swiftly, not from engineering labs, but courtrooms and boardrooms. The SEC launched an investigation into Tucker, alleging fraud. Though the charges were later proven baseless, the damage was done. Investors fled. Suppliers, under pressure from the Big Three, withheld materials. Steel vanished. Parts stopped arriving. Without a supply chain, Tucker's factory fell silent. He managed to produce just 51 cars before the operation collapsed. But those 51 vehicles carried a legacy no courtroom could erase. Many still run today, without engine rebuilds, without major repairs. The 150,000-mile promise turned out to be conservative. Tucker didn't exaggerate. He understated. Preston Tucker's dream died not because it failed, but because it succeeded too well. He was acquitted of all charges in 1950. By then, it was too late. His designs were shelved. His tooling disappeared. The industry returned to business as usual. Engines would continue to fail right on schedule. And yet, beneath the surface, the memory lingered. What happens when innovation refuses to play by the rules, when durability becomes defiance? Tucker didn't just build a car, he built a question. What if things could be made to last? That question still echoes. In garages where Tucker 48s idle quietly, in the quiet defiance of an engine that never asked for repairs, in the uneasy knowledge that sometimes progress is less about what we build and more about what we bury. Preston Tucker didn't lose to engineering challenges. He lost to the discomfort of a world not ready for reliability. In his defeat, we glimpse a greater truth. Sometimes, it's not failure that ends a dream, but success. What if a single drop of fuel could take you farther than the industry ever allowed? In the dry wind of a 1930s Canadian summer, a car rolled across open roads from Winnipeg to Ottawa, over 1,400 miles on just 15 gallons of fuel. Behind the wheel was Charles Nelson Pogue, a quiet mechanic with an extraordinary invention, a carburetor that vaporized gasoline so completely It transformed combustion efficiency. Witnesses were stunned. Reporters documented it. Officials watched it happen. The math didn't lie. Over 200 miles per gallon. The secret? Heat. Pogue's design used waste exhaust to warm the fuel into a vapor before mixing it with air. In traditional engines, much of the fuel remains in liquid droplets, inefficient, incomplete. But with full vaporization, the explosion inside the cylinder is cleaner, more powerful, more complete. It was simple, elegant, genius. He patented the design in both Canada and the US. The documents still exist, their diagrams etched like blueprints to a forgotten future. There were no exotic materials, no advanced electronics, just a smarter way to use the fuel already in your tank. In 1936, Pogue demonstrated his carburetor before executives from the Ford Motor Company. They saw the numbers, they watched the car go, interest sparked. Then, just as quickly, it vanished. Enter the oil companies. A car that used 90% less fuel wasn't just an invention, it was a crisis. Gasoline sales, the lifeblood of a growing oil empire, would collapse. Profits would plummet. Infrastructure built on endless consumption would be obsolete overnight. The offers came. Money, silence, influence. Stories vary. Some say Pogue was bought off. Others say he was threatened. Some claim he sold the patents under conditions that ensured they'd never be used. What's clear is this: the carburetor disappeared. Pogue walked away. He spent the rest of his life working on other ideas, never returning to the one that had changed everything. You can still find his patents. You can even try to build one. But no one has reliably replicated the results. Maybe the documents leave out a crucial step. Maybe the demonstrations were exaggerated. Or maybe, and this is harder to admit, the technology worked and was simply buried. A car that could travel 200 miles on a gallon in the 1930s would have rewritten history. Even half that efficiency would have rocked the automotive world. But efficiency is dangerous when profit depends on waste. What's efficient for the user is often devastating for the supplier. The Pogue carburetor became a legend whispered among mechanics and dreamers, a symbol of how close we came, of what might have been. And so we return to the same haunting question. What do we do with a technology that threatens too many profits? Sometimes we shelve it. Sometimes we buy it. Sometimes we erase it. In the case of Charles Nelson Pogue, we simply let it drift into obscurity, quietly, methodically, completely. But the road remembers. The machine remembers. And somewhere, in a garage filled with dust and possibility, someone still asks, what if the car was telling the truth? The steam that once powered locomotives, factories, and cities could have powered your car. At the turn of the 20th century, American roads echoed with the soft hiss of steam-powered automobiles. Among them, none was more elegant or more feared than the Stanley Steamer. Built between 1902 and 1924, these cars were fast, silent, and astonishingly reliable. In an age of sputtering gasoline engines, the Stanley glided forward with serene power. Steam delivers instant torque. Unlike internal combustion engines that need to rev and build momentum, a steam engine produces full power at 0 RPM. In 1906, a Stanley set the land speed record, 127 miles per hour, blowing past the clunky gas-powered competitors that struggled to hit 60. But raw speed wasn't its only advantage. The Stanley's engine required little maintenance. There were no spark plugs, no pistons, no complex valve trains. With fewer moving parts, there was less to break, and steam engines could run for hundreds of thousands of miles without a rebuild. Some Stanley cars, built in 1910, were still running smoothly in the 1950s. Fuel, flexible. The Stanley could burn kerosene, gasoline, alcohol, even wood. In a world increasingly tethered to oil companies and their chosen fuels, the Stanley offered something radical: independence. So why did it vanish? The official story is one of convenience. Gasoline cars became easier to start. Steam required time, several minutes to build pressure. But by the 1920s, Stanley had solved most of that. Startup times had dropped below a minute. The real story lies elsewhere. The Stanley Steamer was a threat, less to the mechanics of combustion than to the economics of it. Oil companies didn't want cars that burned cheap kerosene or wood gas. They wanted a captive market dependent on gasoline. Steam cars, with their open fuel menu, broke that dependency. Worse, they lasted too long. An engine that runs for 40 years without major repairs doesn't generate sales. It doesn't bring customers back for parts, service, or new models. It breaks the cycle. The Stanley brothers didn't just face market headwinds, they were swamped by legal battles. Patent lawsuits, many backed by oil-connected interests, tied up the company for years. In 1917, Francis Stanley died in a car crash. Without his leadership and under constant pressure, the company faltered. By 1924, it shut down. But the cars lived on. Even today, a few Stanley Steamers still run, quiet as whispers, smooth as wind. They are reminders of a different philosophy: build something that works, and works for a lifetime. In the end, the Stanley engine's flaw wasn't mechanical, it was philosophical. It cared too little about repeat business. It asked too little of its owners. It trusted the machine and the driver to go the distance. In a world obsessed with speed, the Stanley offered something rarer: stillness, simplicity, and time. Its steam has long since evaporated from the roads, but the memory lingers. What if the future had been quieter, cleaner, less dependent on a single fuel? We had that choice once, and we chose something else. It had only one moving part, and that was one too many. In 1996, General Motors unveiled the EV1, the first mass-produced electric car of the modern era. Sleek, silent, and years ahead of its time, the EV1 looked like a spaceship on suburban streets. But beneath its futuristic shell lived a motor so simple, so resilient, it posed a threat far beyond the garage. The heart of the EV1 was an AC induction motor. It had no pistons, no spark plugs, no timing belts, no valves, just a rotor. One moving part. With regenerative braking, even the brake pads lasted forever. Owners reported minimal wear after tens of thousands of miles. Oil changes? Not needed. Tune-ups? Irrelevant. The motor could run for 500,000 miles with almost no attention. The driving experience was smooth, responsive, and quiet. Torque arrived instantly. Maintenance costs plummeted. Service visits became rare. The EV1 didn't just represent a new car, it represented the end of an era. The mechanical symphony of combustion replaced by the quiet hum of electricity. Customers loved it. Waiting lists formed. Leaseholders begged GM to let them buy the cars outright. But GM refused. And then the unthinkable happened. They took them all back. Under cover of night, EV1s were rounded up and crushed. Crushed. Not sold, not stored, not repurposed. Destroyed. A few were spared, sent to museums with disabled drivetrains. Their motors, too, were destroyed, lest someone figure out how to use them again. GM cited lack of demand, but the demand was real. The real reason was fear. Fear of a motor that would never break. Fear of a car that didn't need oil. Fear of what it would do to the industry's most profitable pillars: service, parts, fuel. Automotive dealerships make more money from repairs than from selling cars. The EV1 offered no repairs to sell. Oil companies stood to lose billions in gasoline revenue. An electric car doesn't pull up to a pump, it plugs in at home. The EV1 represented independence. From oil, from dealerships, from the scheduled breakdowns that sustained a trillion-dollar ecosystem. And so, the motor had to go. GM didn't just eliminate a vehicle, it sat on the patents for the motor and battery management systems. Other automakers couldn't license the technology. They had to reinvent the wheel, literally. Tesla would later build its empire on similar ideas, but they had to work around the legal ruins GM left behind. What makes the EV1 story so unsettling is its clarity. There was no ambiguity. The motor worked, the car worked, the customers were ready. And yet, it was erased, not by failure, but by deliberate extinction. In a different world, we'd be driving vehicles with motors that last as long as we do. We'd measure maintenance not in miles, but in decades. But that world asked the wrong question. What's good for the driver? The industry asked something else. What's good for business? And the answer, quietly, efficiently, was not the EV1. Somewhere in a desert lot, buried beneath twisted metal and broken glass, lies a motor with one moving part. It moved too well, too long, and so it does not move at all. It smelled like freedom, faintly sweet, a hint of fryer oil drifting behind a rumbling diesel engine. In the 1970s, German engineer Ludwig Ellbert built a machine that could run on nearly any oil, diesel, vegetable, even used cooking grease. His engine didn't care where the fuel came from. As long as it burned, it powered forward. It was a marvel of design, multi-fuel by intention, efficient by nature, and, most dangerously, independent of oil. The Ellbert engine used a unique combustion chamber and injection system that accommodated fuels with wildly different properties. Most diesel engines sputter or fail when fed anything but refined petroleum. Not this one. Farmers ran it on sunflower oil. Mechanics used fryer grease. Trucks drove hundreds of thousands of miles without touching a drop of fossil fuel. It was not a theory. It was not a prototype. It was real, and it worked. Ellbert converted cars, tractors, generators. Customers reported exceptional fuel economy and reliability. Maintenance costs dropped. Fuel bills nearly vanished. For the first time, everyday people could grow or reuse their own energy source. The fuel supply chain could begin and end at a local restaurant or field. But freedom has a cost, and the Ellbert engine crossed too many lines. Oil companies saw a direct threat. If engines ran on vegetable oil, who would buy diesel? If waste oil became fuel, how could petroleum remain essential? The response was subtle at first. Regulations began to tighten. Countries started taxing vegetable oil at the same rate as diesel, removing any economic incentive. Fuel standards were rewritten to disqualify alternative oils. Suddenly, it was illegal to run your car on what your kitchen threw out. Major automakers refused to license the technology. Not because it didn't work, because it worked too well. A car that didn't need fossil fuel disrupted too many relationships between suppliers, governments, and manufacturers, between profit and control. Ellbert tried for decades to break through. He pitched Mercedes, Volkswagen, BMW. No one bit. His engines remained a niche product, cherished by enthusiasts and rural pioneers. When he died in 2003, his company quietly faded. The patents lingered, the knowledge remained, but the momentum was gone. Today, a few hobbyists still convert their vehicles using Ellbert's principles. Some run on used cooking oil, carrying the scent of fries into the morning commute. They're reminders of what could have been. A world less dependent, less centralized, more resilient. The Ellbert engine wasn't destroyed with hammers or fire. It was drowned, slowly, methodically, in paperwork, regulations, and silence. No need for conspiracies when compliance can do the job. What makes this story sting is its simplicity. The Ellbert engine was not magic. It was common sense, applied with elegance. It worked because it respected fuel as a flexible, abundant resource, not a product to be tightly rationed. Imagine a world where fuel came from your community, where energy didn't flow from far-off refineries, but from local fields and kitchens, where engines asked less of the earth and gave more to those who used them. We had that world within reach. It smelled like sunflowers and old grease, and we let it go. It started with a car too big to care about fuel economy and ended with a whisper of genius from a 24-year-old mechanic. In 1977, Tom Ogle took a 1970 Ford Galaxy, a massive V8-powered behemoth, and drove it over 100 miles on a single gallon of gasoline. Reporters rode with him. Mechanics verified the setup. Government officials observed, no tricks, just a fuel system unlike anything they'd seen before. Ogle's invention removed the carburetor entirely. In its place, a sealed chamber that vaporized fuel before delivering it to the engine. Not mist, not droplets, true vapor. The result? Near complete combustion. Less waste, more power from less fuel. Where traditional engines burned incompletely, Ogle's design extracted everything. It wasn't theory, it was on the road, and it worked. He received a patent. Interest surged. Shell Oil, automakers, investors, they all came knocking. Then, almost as quickly, they vanished. Meetings were cancelled. Calls went unanswered. Promises dissolved into silence. And the threats began. His shop was broken into. Prototypes stolen. Diagrams disappeared. He was followed. Shots were fired at his car. Friends reported he looked over his shoulder constantly. He told people he had been offered large sums to walk away. He refused. In 1981, while seeking final investment to bring his system to market, Tom Ogle was found dead. The official report said overdose, alcohol and tranquilizers. But those who knew him said he rarely drank. He wasn't the type. He was focused, ambitious, cautious. At 26, the man who had made engines sip fuel like tea was gone. With him went the invention. His company dissolved. His patents remained, but without the inventor, the heart was missing. No one has successfully recreated the full system, despite the designs being public. Whether the patent lacked key details, or whether the suppression was more subtle, what matters is the result. The Ogle system didn't just improve efficiency, it demolished it. It promised to cut fuel consumption by 70%, maybe more. That's not an upgrade. That's an earthquake. It shook the foundations of oil revenue, automotive design, and even infrastructure planning, and it couldn't be allowed to last. To this day, those who remember Tom Ogle do so with a mix of awe and frustration. He was a mechanic, not a mogul. He wanted to build something better, not disrupt a global industry. But his brilliance stepped over an invisible line, the point where efficiency stops being admirable and starts being dangerous. What if your car didn't need gas stations every few days? What if 100 miles per gallon were normal, not miraculous? What if the barrier was never technology, but permission? Tom Ogle asked those questions. The answers came not in applause, but in silence, in shadows, in an empty garage where a great idea was last seen, idling toward a future we never reached. His car moved forward. The world moved on. It ran not on fuel, but on a difference in temperature, a heartbeat powered by heat and cold. The Stirling engine, first conceived in 1816, doesn't explode anything. It doesn't roar or sputter. It breathes steadily, cycling air between hot and cool chambers, converting temperature gradients into motion. It's quiet. It's efficient. And for a brief moment in the 20th century, it almost changed everything. By the 1970s and 80s, as fuel crises rattled global confidence, major manufacturers turned back to the Stirling engine's promise. Ford, General Motors, Philips, even NASA. They all built working automotive prototypes powered by Stirling engines. These machines used external combustion, burning fuel outside the engine to heat the gas inside. No explosions, no combustion chambers, no pollution-filled exhaust. The numbers were astonishing. Thermal efficiency reached 40%, sometimes more, double what most gasoline engines could achieve. Emissions were nearly zero. The engines ran on almost anything: gasoline, diesel, kerosene, propane, alcohol, even wood or solar heat. With few moving parts and no violent internal pressure, they lasted longer, ran quieter, and required minimal maintenance. You could fuel them with waste heat from another engine. You could drive a car with an engine that whispered. Then, all at once, the projects ended. Philips stopped in the late 70s. Ford and GM cancelled theirs by the late 80s. NASA wrapped up its automotive research quietly. Official reasons varied: costs too high, engines too slow to start, power density insufficient. But those hurdles were engineering problems, and solvable ones. The deeper problem was that the Stirling engine solved too much. It offered durability, fuel flexibility, low emissions, and near silence. It eliminated the need for complex transmission systems because torque could be delivered across a wide range of speeds. It reduced dependence on fossil fuels and upended the idea that cars must be loud, inefficient, and short-lived. For oil companies, it threatened the very notion of fuel as a single-source commodity. For automakers, it endangered the parts and service model. For regulators and planners, it disrupted the assumptions that had built an entire transportation infrastructure. A car that could last decades, burn anything, and require almost no service? That was a problem no one wanted to solve. And so, the Stirling engine became a ghost. Not because it failed, but because it quietly refused to cooperate with the rhythms of planned obsolescence. It lingered in academic papers, in museum displays, in the memories of engineers who had once believed. Today, the Stirling engine survives in niche applications: submarines, satellites, hobbyist kits. It's there, proving itself, over and over. But not under the hood. Its silence was its strength, its simplicity, its crime. What if we had followed that quiet hum instead of the roar? What if cars didn't shout and shake, but whispered and endured? The Stirling engine asked those questions, gently. The answers never came. They were too quiet to hear over the engines we chose instead. It looked like a bundle of metal tubes, nothing special, nothing sacred. But some said it ran on water. Others claimed it tapped into something stranger. In the 1990s, An Australian man named Joe, he gave no last name, unveiled a device that came to be known as the Joe cell. It was deceptively simple, concentric cylinders of stainless steel, wired and submerged in water. No moving parts, no obvious fuel source. Yet Joe claimed the cell could power a car using only water and what he called a natural energy field. To most scientists, it sounded absurd, and yet the demonstrations happened. Television crews filmed his car driving without gasoline. Witnesses reported engines running with disconnected fuel lines. Experimenters around the world built similar devices and shared videos showing engines turning over, sometimes running for hours. The explanations varied: hydrogen production through electrolysis, orgone energy, zero-point fields. Joe himself was evasive, describing it less as a machine and more as a conduit for something unmeasurable. Critics called it pseudoscience, and maybe it was. But even hoaxes reveal something about the world that reacts to them. Because soon, Joe's demonstrations stopped. His workshop was vandalized. He reported thefts. He received phone calls, anonymous, threatening. Men showed up uninvited, warning him to stop. Joe went quiet. His website disappeared. Interviews ceased. He told friends he feared for his life. Whether those threats were real or imagined, the result was the same: silence. No one ever commercialized a Joe cell. No peer-reviewed study confirmed its function. But the intensity of the response, the fear, the suppression, suggested that the device had struck a nerve. What if the Joe cell worked, even partly, even by accident? If an engine could run without conventional fuel, even for a moment, the implications would shatter assumptions. Oil, infrastructure, maintenance, all challenged. And if it didn't work, why go to such lengths to make sure it disappeared? That's the paradox. Invention attracts scrutiny, but suppression often implies danger, not to safety, but to stability. The Joe cell was never proven, but it was never forgotten. In online forums and underground garages, believers still tinker, hoping to replicate the impossible. Maybe they're chasing a ghost, or maybe they're reaching for a truth that science hasn't yet caught. Joe didn't offer blueprints so much as breadcrumbs. He suggested that engines, like people, might be more sensitive to energy than we realize. That motion doesn't always come from combustion. Whether he was right, wrong, or something in between hardly matters now. His cell became a symbol of wonder, of fear, of what might be hiding just beyond the boundaries of accepted knowledge. In the end, the Joe cell wasn't destroyed in court or crushed in a warehouse. It was erased by doubt, fear, and the quiet enforcement of normalcy. And in that erasure, we see something profound. Not every threat to the status quo arrives with proof. Some arrive with a whisper, an anomaly, a question that won't go away. What if water could remember? What if engines could feel? What if the things we dismiss are the ones we should have listened to most? It wasn't sleek, it wasn't flashy, it didn't whisper or shimmer with mystery, but it worked too well. In the 1970s, inventor Samuel H. Ellbert introduced a mechanical innovation he called the Shei engine. It was a simple idea with a complex effect: two cylinders working in opposition, sharing a combustion chamber. This arrangement improved thermal efficiency, reduced mechanical losses, and generated more power from less fuel. Test runs were conclusive. Elliott's engine doubled fuel efficiency compared to conventional designs with similar displacement. The engine was smooth, durable, and far simpler mechanically. With fewer parts, it required less maintenance. With more complete combustion, it wasted less energy. Ellbert secured patents. He attracted early investors. Demonstrations impressed skeptics. The engine didn't rely on exotic fuels or untested science. It was solid engineering, proven, repeatable. Then came the silence. Investors backed out. Contracts dissolved. Promised funding evaporated without explanation. Elliot told colleagues he'd been approached, pressured, perhaps even offered money to walk away. When he refused, support dried up. Without capital, production stalled. Without partners, the project withered. And eventually, so did Elliot's hope. The patents remain. The design is public. But no one has built the engine commercially. Not because it failed, but because it succeeded in all the wrong ways. The Shei engine's crime was its simplicity. It threatened no single industry, but quietly undermined several. Automakers rely on complexity. More parts mean more maintenance, more replacements, more revenue. Fuel efficiency, when extreme, threatens fuel sales, and a more durable engine slows the cycle of consumer replacement. The Shei engine wasn't revolutionary in appearance. It didn't rewrite the rules of physics. It simply followed them better. It asked, what if we burned more completely? What if we moved more smoothly? What if we got more from the same? Those questions should have opened doors. Instead, they closed them. Elliot spent the rest of his life trying to revive interest. He gave talks, submitted proposals, refined the design. But the world had turned away. He died in 2003 without ever seeing his engine reach production. Today, the Shei engine is little more than a footnote in the annals of innovation, a ghost in the patent office, a diagram in an old folder. Yet it tells a story familiar to anyone who's dared to challenge the comfortable rhythm of inefficiency. Sometimes, the market doesn't kill a good idea. It smothers it, gently, quietly, by doing nothing at all. What if simplicity was the threat all along? What if the best ideas are the ones that don't need us, don't need to be serviced, repaired, replaced? What if the answer was never buried, just ignored? The Shei engine didn't fail. It was left behind. And in that abandonment, we're reminded that the world doesn't always choose what's best. It chooses what fits, what feeds the machine. And sometimes, the simplest engine is the one it can never accept. It didn't roar, it didn't shine, it didn't rust. In the 1970s, a quiet revolution began in a place few were watching, within the structure of the engine block itself. Inventors experimented with fiberglass as a material for engines, not the housing, not the trim. The engine, the cylinders, the heads, the heart. The results were startling. Fiberglass engines were lighter than their metal counterparts. They dissipated heat more evenly, reducing warping and stress. They didn't corrode. They could be molded with precision, eliminating machining steps. They ran cooler, cleaner, and quieter. And most importantly, they lasted. These engines weren't theory. Prototypes ran for thousands of miles with minimal wear. The weight savings alone improved fuel economy dramatically. The thermal stability meant more consistent combustion. Some designs even improved power output, thanks to the precision of composite shaping. And then, just like that, they disappeared. No major manufacturer adopted the technology. Research funding dried up. Promising development programs were shelved. The official reason? Fiberglass couldn't handle combustion stress long-term, but the prototypes said otherwise. The engines had already done what they weren't supposed to. The deeper truth was less about engineering and more about infrastructure. Metal engine manufacturing is the foundation of the automotive industry. Foundries, mills, casting plants, billion-dollar investments across continents. A shift to composites would render that infrastructure obsolete. Smaller companies, with simpler tools, could enter the game. Barriers would fall. Worse, fiberglass engines didn't break. They didn't corrode. They didn't need rebuilding. They lasted too long. For an industry built on parts, repairs, and replacements, that was a disaster. A vehicle with a fiberglass engine might run for decades with minimal attention. No gasket replacements, no warped heads, no rusted blocks, just quiet, durable service. The silence that followed was total. No scandals, no lawsuits, no accusations, just nothing. And yet, fiberglass remains everywhere in modern vehicles, except where it might matter most. It wraps bodies, lines trunks, shapes panels, but it never touches the combustion chamber. It's allowed to be cosmetic, never structural, never central. It's hard not to wonder why. What if the barrier isn't what fiberglass can do, but what it threatens? An engine that doesn't decay, a material that doesn't fatigue, a design that doesn't require a global empire of metal and machines to sustain it. The fiberglass engine was never flashy. It never made headlines. But in its silence, it revealed something loud. Sometimes the most dangerous ideas aren't the ones that break the rules. They're the ones that make everything easier. Too easy to control, too easy to last, too easy to live with. We didn't reject fiberglass engines because they failed. We rejected them because they didn't. And because, deep down, we weren't ready for a car that never aged. 10 engines, 10 disruptions, 10 silences, from Tucker's aluminum marvel to fiberglass composites, from vaporized fuel systems to one moving part electric motors. A pattern emerges, not of failure, but of rejection. Again and again, a machine arrives that works too well. And again, it vanishes. The official reasons vary. Funding issues, regulatory hurdles, market readiness, engineering limitations. But dig deeper and you find a consistent truth. These engines didn't fail because they were flawed. They failed because they worked too efficiently, too reliably, too independently. Each threatened a different pillar of the automotive world. The Tucker engine challenged the cycle of replacement. The Pogue carburetor threatened fuel sales. The Stanley Steamer upended fuel dependency. The EV1's motor eliminated maintenance. The Ellbert diesel offered energy independence. The Ogle system shattered fuel economy expectations. The Stirling engine undermined the idea of combustion itself. The Joe cell poked at the edge of accepted physics. The Shei engine reimagined internal combustion efficiency. The fiberglass engine questioned the necessity of metal. Together, they form an unintentional chorus, a symphony of solutions stifled not by ignorance, but by inertia. Because in the modern economy, durability is dangerous. A car that lasts 500,000 miles without major repairs erodes dealership service profits. An engine that sips fuel makes gas stations obsolete. A machine that needs no oil change doesn't return to the shop. An engine that burns vegetable oil doesn't feed the fossil fuel machine. These innovations didn't vanish in fire or scandal. They were smothered by red tape, by silence, by convenient timing. Patents were bought and shelved. Programs were cancelled in unison. Inventors were offered money to walk away, or threatened when they wouldn't. Some disappeared. Some died. The world did not cry out. Most never knew. And maybe that's the most haunting part. How easy it is to lose something that could have changed everything. Not through malice, through momentum, through systems that reward short lifespans and punish longevity, through economies that value recurring problems more than lasting solutions. But the stories survived, in old newspaper clippings, in dusty garages, in quiet online forums, in patents no one used and engines no one finished, in memories whispered from one curious mind to another. They are not gone. They are simply waiting, waiting for a world that no longer measures success by what breaks down, but by what endures. Waiting for an economy that sees value not in the next transaction, but in the lifetime of trust a machine can offer. Waiting for us to ask, what if we built not for the market, but for the road? This isn't just about engines. It's about time, about how we choose to spend it, how we shape it, and how we allow it to shape us. The past gave us glimpses of what could have been. The question now is, will we recognize it next time it arrives? Will we be ready not just to build what lasts, but to keep it alive? The engines we lost weren't just mechanical, they were philosophical. Each invention carried with it a vision, not only of efficiency or longevity, but of a different relationship between people, machines, and the systems that bind them. They invited us to imagine a future where technology served quietly, faithfully, and for far longer than expected. But those futures conflicted with the logic of planned obsolescence. A car that runs forever does not encourage new sales. An engine that burns any fuel doesn't protect the supply chain. A system that maintains itself doesn't feed the service economy. Profit margins demand friction, breakdowns, refueling, replacements. Inconvenience is the business model. And so invention was not enough. To survive, these engines needed more than engineering. They needed acceptance, infrastructure, advocacy. They needed a society willing to shift not just how we build, but why. That's where the story fractures. Because as a culture, we embraced progress as novelty, not endurance. We praised the new over the necessary. We replaced what still worked in search of something shinier. In doing so, we sometimes discarded the better machine. But in each of these discarded engines lives a lesson. The Tucker engine showed that reliability is revolutionary. The Pogue carburetor proved efficiency can be dangerous to monopolies. The Stanley Steamer reminded us that the best solutions might be the oldest. The EV1 motor warned that simplicity threatens complexity's profit. The Ellbert diesel championed local renewable independence. The Ogle system whispered that we've always had more than we're told. The Stirling engine revealed that silence can be strength. The Joe cell challenged the boundaries of belief itself. The Shei engine asked whether elegance could ever be allowed to thrive. The Fiberglass engine demonstrated that lighter, longer-lasting, and cooler-running machines were already within reach. And then each, in its own way, was removed from the road. Not because the science failed, but because the systems refused to adapt. Today, we stand in a new era, facing ecological urgency, economic uncertainty, and technological acceleration. The engines of the past speak directly to these moments. They offer more than nostalgia. They offer blueprints, both literal and symbolic, for a different way forward. A way that prizes longevity over churn, simplicity over spectacle, function over fashion. We can still listen. We can still learn. Not by resurrecting old machines for novelty's sake, but by honoring their intent, by designing with care, by asking what kind of future we truly want to drive toward. The road ahead doesn't have to repeat the past, but it can remember it. The engines never broke down. We did. And the question remains, are we ready to build again? Not just with metal and fuel, but with purpose. The machines are quiet now. In garages and barns, under tarps and dust, remnants of a different future sit idle. Not broken, not defeated, just forgotten. They remind us that technology has never been just about gears and wires. It has always been a mirror. What we build reflects what we believe. And somewhere along the way, we believed that things shouldn't last. We built engines to wear out. We designed systems to fail. We turned maintenance into business, inefficiency into strategy. And when someone dared to ask, what if this ran forever? The world politely looked away. But even silence leaves echoes. The hum of an electric motor with one moving part. The hiss of a steam engine that burns anything. The purr of a diesel fed by sunflowers. These are more than sounds. They're ideas, living proof that endurance was never out of reach. The suppression wasn't always malicious. Sometimes it was inertia, sometimes fear, sometimes just the weight of too many habits. A system that feeds on repair cannot digest perfection. Yet here we are, facing climate breakdowns, resource scarcity, rising costs, and the fragility of global supply chains. Suddenly, the things we once cast aside, durability, flexibility, simplicity, look like salvation. The engines that never broke down offered a glimpse of that salvation. And though they were buried, their message remains. We can build things that last. We can choose independence over dependence. We can align innovation with integrity, not just income. The real tragedy isn't what was lost. It's how easily we let it go. And yet, it's not too late. The blueprints exist. The knowledge persists. The ideas still circulate. In forums, in patents, in the minds of those who refuse to forget. The path back is not simple, but it is visible. And it begins with remembering what we already proved was possible. So this story ends not with an engine, but with a question. What else have we built only to bury? And what would happen if this time we chose to keep it running?